refer to. Well, one problem with following Georgi to the letter is that Georgi has a sort of mishmash of notation. And essentially, he does what he thinks is best for physicists. So jumps into a physicist's familiar notation too soon. And sometimes that sort of becomes a bit confusing, at least to me. I tried to straighten out the notation myself while preparing for this lecture, but since I didn't really give myself enough time to prepare, I think that I will sort of still perhaps be a bit confusing in the notation, but I hope everything will get through anyway. So let's basically talk about what we were doing before. You remember we were essentially talking about things called roots and weights. Well, weights are generic roots are special kind of weights actually. And the basic idea was that if you have a representation of a Lie algebra, then of course means you have representative linear operators which obey the same commutation relations as the Lie algebra does. And these linear operators of course act on states, some vector space. And basically the representation essentially is the description of how the operators corresponding to the Lie algebra elements act on the vectors. So in a particular representation, you have a vector space. You have operators which act on the vector space, and it's the operators which obey the same commutation relation as the abstract Lie algebra elements do. And in particular, so if you talk about a particular representation, so let's call that representation D. I'm just following Georgi here. So because my Lie algebra has a bunch of operators, bunch of elements which commute among each other, and these are called the kata generators, or basically the generators of the kata subalgebra of the Lie algebra. You'll have corresponding operators for them, H1, H2 to Hn. So these are, well, this is where the confusion of notation sort of becomes apparent. You can also, yeah. Do you have a question?
Sir, I had a question. In the last class, while dealing with this, we took J1, J2, J3 as example, and J3 formed a Kata subalgebra, and we did all the analysis.
Yeah.
So, I mean, there we had like, so in general, do we just take one subalgebra and do all the rest of the analysis based on that, or can we take all the subalgebra simultaneously?
No,
and
the
do
point
the
is
same
taking any other subalgebra does not give you anything new. Once you have got the Kata subalgebra, okay, this is the proof of that is not trivial. But
no, I mean,
yeah.
What if you have multiple Kata subalgebras?
You can't have multiple Kata subalgebras. What you can have, at least not for semi-simple Lie groups, the kind that we are dealing with. In a semi-simple Lie group, you can have one Kata subalgebra. You can have, of course, multiple isomorphic copies to that. That is, instead of J3, you could have just as well taken J2. The structure of J2 would be exactly identical. So that would be an isomorphism. You could map J3 to J2. And that would give you exactly the same structure. Okay. So basically what you do is take a maximal set of generators or set of elements, not really generators. Generators are basically basis elements. But when you take maximal set of elements of the Lie algebra which commute among each other, you get a subspace or subalgebra. That subalgebra is called the Kata subalgebra. There, of course, would be multiple such Kata subalgebras corresponding to different choices of the generators you're taking, but they will all be isomorphic to each other.
So this is true only for semi-simple Lie algebra?
Yeah, this is specifically true for semi-simple Lie algebras. For others, it's not that easy. Which is exactly why semi-simple Lie algebras are easier to deal with. However, most of the physically important ones are semi-simple Lie algebras, and they sort of give us enough to keep us busy anyway. Mathematicians, of course, deal with more general cases. They have to. Physicists go more into the depth of semi-simple algebras because that's almost all the examples that are of importance for us. Almost, not always, but this is good enough for most purposes. So what I was saying is, in the Lie algebra itself, if I use small letters to denote elements of the Lie algebra, but I will not because soon George also changes the notation. But if I did that, there would be generate elements in the Lie algebra which commute among each other, which have a Lie bracket which is 0. And corresponding to that, you will have general operators in your representation, capital H1, capital H2 up to capital Hm, which for convenience we can always choose to be Hermitian, because we are only talking about unitary representations and we can make the generators Hermitian if we want to. And they obey the property that Hi, Hj commutator is 0 for all I, j belonging to 1 to n. That's simply a reflection of the fact that the representation operators have to obey the same algebra as the original Lie algebra. That's of course what it means when you say it's a representation. Okay. And what we can always do is by the way, there's another thing, because these are operators and because we want to talk of lengths of these things soon, we need to define a norm on operator space. Now, how do you define a norm on operators? The answer is typically you would take, or how do you define a distance or an inner product? If you once have an inner product, you can always define a distance. The two operators A and B, one way to define a norm is take this. Trace of A dagger B, and can easily show that this has all the properties of, this is an inner product. It shows all the properties of an inner product in the sense that it's linear in one factor, the second factor. It's linear in B, and then it obeys this, which has various names. Sometimes you call it anti-commutativity, but that's sort of confusing because that sort of makes you think that A comma B is minus B comma A. This is also called the Hermitian conjugate property or the Hermite property. This is standard for inner products in a complex vector space. Okay, and of course A comma A, case of A dagger A, can easily check that this has to be non-negative and is 0 only when A is 0. So all the properties of the inner product are satisfied, and as a result you can define norms and lengths using this. And this is one of the standard norms that you use when you're dealing with operators. It's called the trace norm. Of course, in an infinite dimensional vector space, you would have to be worried about whether this trace norm at all converges, and all kinds of additional issues would have to be worried about. But since we are talking of finite dimensional representations here, these are operators in a finite dimensional space. The trace norm the trace norm basically becomes a trace of product of matrices, finite matrices, and that's a perfectly well-defined object. So we don't really have to worry about such things here. And the normalization that is chosen that you can choose it. You could have chosen it, the normalization like this. That is, after all, remember, since H1, you have M generators, right? These are basis vectors for the Karta subspace. Now, you can of course choose other linear combinations. In particular, you can orthogonalize, because if H1, H2, Hm commute with each other, any combination also commutes with each other. You can always choose an orthogonal version, right? That's just the Gram-Schmidt orthogonalization procedure. You just orthogonalize. If they were not originally orthogonal, you can orthogonalize them. And you can always choose the scale to be 1, but usually what you do often is that you don't choose it to be 1 because of convenience. Sometimes some other norm is convenient. So you choose them all to be equal length, but the equal length k is some constant, which can depend on the particular representation that you're talking about. This KD is simply for convenience, especially because in physical applications, sometimes the normalization is dictated by other things, not by geometric convenience like you want unit length, but by, say, if you're using SU3, for example, you will find some physical quantities connected with these HIs. Of course, they are commuting. Remember that they are in a quantum mechanical scenario, there would be commuting Hermitian operators. So there would be observables which are simultaneously measurable. So what you would like to have are observable quantities which can directly assign to them. And although frankly 3 times an observable is also an observable, usually because you have some kind of physical significance given to some observable quantities already, you don't have the freedom to choose your lengths as you go. So depending on the representation, you may want to choose different lengths. So that's why this constant is there. It really is not of much consequence. It's a some positive constant. That's all you really need to worry about. And it's a constant for a particular representation. Okay. Now the important thing is this. Because all these HIs commute, they are commuting operators. As I just said, if you have a commuting bunch of operators, then you will have simultaneous eigenstates. So what you can have is a situation, you can have an state mu, which is labeled by the eigenvalues of HI, as happens in all situations when you're using commuting observables. Of course, it depends on which representation you have, and it might also, depending on your physical scenario, it might depend on other labels. So that is, you may still have degeneracy after you have labeled all the eigenstates with their eigenvalues. So you may want to have other labels as well. Okay. But the important thing is this state, which is labeled by this quantity mu, and let's put an arrow on top of mu because mu is really a vector quantity, as you will soon see. So basically, mu I is the eigenvalue corresponding to HI. And the important thing is because the HIs commute with each other, the mu I's, so you can have a simultaneous set of eigenvectors, and these mu I's, there are of course as many mu I's as there are Karta generators. This is called the weight vector for this particular eigen. So these states are often called eigenstates of weight, and the mu vector is called the weight vector, and mu I's are called the weights.
What's D?
D is just whichever representation you're talking about. So different representations, of course, have different. In fact, if you are using a different representation, then this HI, although I'm writing it as HI for all representations, the operators are also, of course, going to be different, right? Not the same operator necessarily. Different vector space, different operators acting on those vector spaces. Okay, and mu I is just the eigenvalues. They are called weights in this particular case. In general, the weights are general eigenvectors, simultaneous eigenvalues of all the Karta generators. Okay, and because there are m of them, you can write them in an m-dimensional. So mu vector belongs to basically Rm, and you can use notations like this. Standard way, mu dot nu is mu1 plus mu2, nu2, etc. By the way, these are Hermitian operators, so all the eigenvalues are real. So that's why it's in Rm, and you are essentially dealing with a real m-dimensional vector space vector here. Okay, please don't get confused about this. There are way too many vector spaces in this picture. There's one vector space which is carrying my representation, and of course, for every representation, there will be different vector spaces carrying that representation. That's point number one. Point number two is, on the other hand, for any given Lie algebra, there is a Karta subalgebra which has m elements. That number is fixed. That's the rank of the Lie algebra. And corresponding to that, you have weight vectors, which are vectors in this m-dimensional vector space. Okay, so that's m-dimensional no matter which representation you're talking about. In every representation, you have an m-dimensional vector. For corresponding to every representation, there's an m-dimensional vector. The vector space is for every representation. But corresponding to any given representation, there are specific vectors in that vector space which carry the simultaneous eigenvalues of the HIs. Okay. Now the important thing is, because the HIs have to mimic the Lie algebra, that is, they are representatives of the Lie algebra after all, these eigenvalues cannot be any arbitrary thing, right? We have already seen that, say for SU2, we have seen that the eigenvalues can, of course, there the vector is only one dimensional because you have only one Karta subalgebra element, only one eigenvalue, but that eigenvalue cannot be anything, right? It cannot be 1.37, for example. There are only certain possible values. Okay. So what we are going to do is we are going to try to understand how the Lie algebraic structure restricts the possible weights that you can have. Is that clear? That is the aim. Ultimately, this is giving us a notion of weights. Because of the Lie algebra underlying the whole thing, the weights cannot be arbitrary, and we are trying to talk about that. Okay, let's take a look at. So so these are weights. So what are roots? Roots basically are weights in a particular representation called the adjoint representation. And what is the adjoint representation? The adjoint representation, after all, every representation, remember, has to have a vector space on which the elements will act. And every Lie algebra carries with itself a vector space. It's the vector space itself, right? Remember, any Lie algebra is already a vector space. Okay, this should begin to remind you of something we did with groups, right? In groups, we said even for groups, when you want a representation, what you need is a vector space. And we said, okay, every group will carry with itself a vector space, which was also obvious. You have to define a vector space where the group elements were themselves the basis vectors, right? That's how we got the regular representation. The adjoint representation is to Lie algebras what the regular representation is to groups. But here, we have life a bit more simple for us, for the simple reason that the Lie algebra already comes with a vector space structure which is automatic. And so we don't have to sort of artificially produce a group algebra that we had to do there. If you remember our discussion on regular representations. And the important thing is, there's something again which we talked about, that it's called the adjoint representation because corresponding to every Lie algebra element, there is an adx, and what is adx is the operator which acts on the Lie algebra elements. The adx y is by definition y, and we already showed that this map x goes to adx is a Lie algebra homomorphism. It obeys or mimics the Lie algebra structure this way. Whether you take the bracket first and then take the adjoint, or take the adjoints first and then take the bracket, you get the same result. This, remember, was a consequence from Jacobi identity. I hope everybody remembers that. So, what you have is a scenario like this. You can talk of adx acting on y. So, where y are the Lie algebra elements themselves, and this is the adjoint representation, where we have operators which act on the Lie algebra elements themselves. And because the Lie algebra elements themselves, remember the way we got that out of Lie groups, was that Lie algebra elements themselves were operators, right? So adx in a sense is a super operator which acts on operators. But as I've already explained before, and I'm pretty sure all of you understand, operators, that is these operators, They form a vector space of their own, and this is just an operator acting on that vector space. Well, the notation which Georgia uses is this. That is, because he of course wants to make it more physicist friendly. So the Lie algebra elements, which are actually operators or they're just vectors, he uses the ket notation for that. Of course, that makes it consistent with the general notation that you're using. Your vectors on which operators act. And what he's saying is, since the generators themselves act, so let's say X acting, the generator X acting on a state given by generator Y, which really is the same as X comma Y. But the notation he uses is this. Because add X comma Y really means X comma Y. The notation he uses instead of add X comma, instead of introducing the adjoint operator, the notation he uses is this. X acting on the state Y gives us the state corresponding to X comma Y. Okay? This is just a notation. It just means the same thing as add X comma acting on Y gives you X comma Y. Because Georgia has not really formally introduced or does not really use the adjoint representation in this sense extensively, he has to fall back on this notation, which I find a bit irritating, but I think it's sort of easy to understand. So, in this notation, can anybody tell me what this is going to be? This really means, at the back of your mind, you should always think this is add HI acting on HJ, which is, of course, commuter of HI with HJ.
K to delta IG identity.
No, this will be 0. You're confusing this.
Oh, yes, sir.
The inner product of HI with HJ with the action of HI and HJ. And that confusion, I agree, because especially because, well, Georgia doesn't even use the inner product notation like this. This is the notation he uses. Simply to conform to phasist choices. Then it might become even more confusing to see that this is delta ij. Well, delta ij times lambda, where lambda is again a normalization constant. He uses lambda specifically for the adjoint representation, but that's fine. This constant, of course, depends on the representation, so he uses lambda for the adjoint representation. This is the inner product of the states of the operators hi, hij. Here, this really means the adjoint hi acting on the generator aj, and that of course is going to give you 0 because they commute. These are two different things, so please don't confuse the two. Okay. Now, coming back to, okay, let me just quickly use the add notation just to say that what does this really tell you? This commutator is 0, right? Because this is actually add of hi comma aj. So because this commutator is 0, what does this tell you? It tells you that add hi's can be simultaneously diagonalized. So it should be possible for you to find out elements in the Lie algebra. Remember, the vector space which is carrying this representation is the Lie algebra itself. So it should be possible for you to find out elements in the Lie algebra. Let's call those elements E alpha, such that add hi acting on E alpha will be E alpha times a number. And those numbers, in fact, the alpha label, okay, let's put an arrow on top of alpha to remind ourselves of that. So the alpha label is simply the corresponding eigenvalue, or in the commutator language, this is what this is going to be. So just to remind you, that's the parallel. In SU2, you have, this is your only Karta element. And of course, it's diagonalizable. And what you're really diagonalizing is not J3. What you're diagonalizing really is add J3. This is add J3 acting on J plus minus is plus minus J plus minus. So I found out eigenvalues of J3, which are J plus and J minus with eigenvalue. We say eigenvalues of J3, but they're really eigenvalues of add J3. Or eigenvalues of the representative for J3 in the adjoint representation, which gives you plus minus J plus minus. Plus minus 1 are the eigenvalues there. In general, for the general D algebra, you will have multiple Karta generators. You will have eigenvalues corresponding to each one of them. And this alpha vector is just a label which carries all of these together. So these are nothing but weights in the adjoint representation, and they play a special role, and they are called roots. The roots are nothing but weights in the adjoint representation. But it's easy to see that because the adjoint representation is specifically about the Lie algebra itself, the roots must have some special significance. And they essentially contain all the information that you want to know about the Lie algebra. And that's what we are going to try to establish, maybe over this class and the next couple. That if you know the roots, in fact, you will soon see that you don't even need to know all the roots. You need to know part of them to be able to find out the entire Lie algebra. Okay. So, well, either you say add hi e alpha is alpha I e alpha, or use Georgi's notation, which goes hi acting on the state e alpha is alpha I e alpha, which means exactly the same thing. Or, of course, all of these mean this for the commutator. Okay, I will often drop the arrow on top of the alpha. I'm going to always assume that if I say alpha, you understand that there is an m-dimensional vector that we are talking about. And its components, alpha 1, alpha 2, alpha n, are the roots, and the root vector is the entire set. Okay. The immediate consequences of this equation. If you take the adjoint of this, what happens? Hi is adjoint, E alpha vectors adjoint. What is this going to be? What is this going to be?
Minus alpha I alpha dagger.
Exactly, because that's a general result which follows from the fact that A comma B is daggers adjoint is B dagger comma A dagger. So E alpha dagger can be identified with E minus alpha. I'm dropping the arrow sign on top of the alpha. Too much bother to write. Right? It's basically that if you have a simultaneous eigenvector like this, you have a corresponding. So if alpha is a root, minus alpha is also a root. Okay. I can find out the simultaneous eigenvector. The generator corresponding to minus alpha is just the adjoint of the generator corresponding to alpha. Okay, there are too many adjoints here, the adjoint representation, the Hermitian adjoint property. So but I hope from the context it's clear which one I mean at any given stage. And among these simultaneous eigenstates, E alpha, E beta, you can always because these are simultaneous eigenvectors of Hermitian operators, remember. What is going to happen is that there have to be conjugates. Okay, you should really check that. You should check that the add HIs are actually Hermitian operators under this norm. But it's pretty easy to check, so I will leave you to check that. Because they are Hermitian, they can be always orthogonal. They are orthogonal automatically, and they can be always orthonormalized. So you will assume that this has been done. But delta alpha beta, of course, means This is 0 unless all the components match. Alpha 1 equals beta 1, alpha 2 equals beta 2, and so on. So that's just a choice. You can always choose to normalize your operators this way. Okay. Now, why are these generators so important? These simultaneous eigenvectors of all the HIs. Answer simply lies in this fact. Let's now go back to an arbitrary representation. Okay, so what we did was we talked about arbitrary representations at the beginning, said that all the HIs in that representation, whatever stood for HIs, will commute, so they will have simultaneous eigenvectors. Now, then we specifically went to the adjoint representation, where the same thing happens. All the corresponding generators corresponding to HIs will commute, but those are the add HIs. So they will have simultaneous eigenvectors, and these simultaneous eigenvectors in this case will also be elements of the Lie algebra, and the simultaneous eigenvector property essentially becomes this commutator property. Now that, of course, is of great importance because, as you have all seen, using commutators makes life a lot easier in many situations. So take E alpha act on mu d. Okay, I'm just dropping. Remember, this was our notation for the state. The root vector essentially gave you what the eigenvalues are. D just labeled the representation, and there would have been extra labels if there are more labels you need to specify the state. For the timing, I'm just dropping them because that's not important for the Lie algebra part of the game. So, and I'm not putting arrows on top of each one of them. These are all m-dimensional vectors. So if you apply E alpha, when I say apply E alpha on mu d, remember what I really mean is E alpha is a Lie algebra element. There is an operator corresponding to that in your representation, so you're really applying that operator on your state mu d. And then you apply HI on that. Again, operator corresponding to HI. But very often, usually we don't make the distinction of operator corresponding to this and the thing itself. Right? When we say J3 acts on Jm, you don't really say the operator representative of J3 acting on the space spanned by the 2j plus 1 vectors and so on. We just say J3. We are just going to use that language. Now this, happily enough, can be easily found out by using this fact. And the commutator, we know the commutator is alpha I E alpha. And here HI goes on acts on mu, so I know it's giving you mu I. So HI acting on that is mu plus alpha's ith component acting on E alpha mu. So given a weight mu, what this process does is produces a new weight mu plus alpha from that. And of course, I can keep on repeating this over and over again, and I can keep on getting newer and newer weights. So more and more independent states in your system. Of course, I did this with E alpha. With E minus alpha, I would have got mu minus alpha. And if I kept on repeating E minus alpha, I would have got mu minus 2 alpha, mu minus 3 alpha, and so on. This should be very reminiscent of what we did with SU2, and it should really be that. Okay.
Sir, in this case, the HI in the HIE alpha is not the adjoint representation. It's just the
no. There is a generator in that particular representation. Remember, when you're talking of any representation, and you say as an operator of that representation, it has to be that, right? It can no longer be the adjoint representation. But the important thing is, commutation relations must be respected in any representation. That's what a representation of a Lie algebra means. For every Lie algebra element, you have a corresponding corresponding operator, and whatever the Lie bracket of the original elements is, the corresponding operators will have to obey the same Lie bracket, which is why this hi is not that hi up there. And this E alpha is not that E alpha. This hi is an operator corresponding to a small hi. This E alpha is an operator corresponding to E alpha. But their commutator is the same as the commutator of the original hi E alpha. At least corresponds to the commutator of hi E alpha. That is why this thing still works.
Okay.
Okay. And because of that, we don't keep on saying that the operator corresponding to V sort of say hi. Basically, that's the whole point of using a representation, that you have the same algebraic structure built in already. Okay. So so basically, what we see is if you have a state, okay, so mu d on which E plus minus alpha, let's do both of them, and hi acts on that, that gives you mu plus minus alpha ith component E plus minus alpha mu d. That's just what I said a while ago. Now, if you look at specifically the adjoint representation, remember what has happened is, in general, what you have in any representation, you have a weight, and hitting with E plus minus alpha shifts them by roots, right? Okay. So whatever weights you have in your representation, you get new weights in that representation by shifting them by roots. As you will soon see, this shifting cannot be arbitrary. There will have to be some limits to that. But essentially, this is how the roots become very important. No matter which representation you are in, essentially the weights of that representation, all the vectors which essentially tell you what that representation is, are related to each other by shifts through the roots. So if you know the roots, you will know a lot. In fact, you know all of everything, but that's something you're going to slowly establish. Okay. Now, in the adjoint representation, if you go back there, look at this thing. So this remember corresponded to a root, which is of course a specific weight in that representation of minus alpha vector. So this is shifting it. So what should happen to this? In any representation, if you have a weight mu, a state with weight mu, and you hit it with E alpha, you are going to shift the weight by alpha. So what happens here?
Shifts by minus alpha.
No, this is minus alpha already. It shifts by alpha. So what happens to that?
0.
It becomes 0. But 0 means what? 0 means it must have a root
It
of
should
0.
vanish when hi acts on it.
Yeah, it should be have a root of 0, which means it should be something on which hi's action gives you 0. So this is a Georgi version of the notation. What this really means is add E alpha, acting on the state which is E minus alpha, this is 0. Okay. But what that tells you is that E alpha comma E minus alpha, which really is what this is, this commutator, must have the property that this commutes with every one of the hi elements. So what does this tell you about this thing? E alpha, E minus alpha commutes with hi for all the hi's.
Same eigenvectors.
Hmm?
Eigenvectors will be same, like simultaneous eigenvectors.
No, This is already a simultaneous eigenvector of all the HIs, but they are simultaneous eigenvector corresponding to eigenvalue 0. So what does it tell you about this specifically? Something which commutes with every Karta generator. What exactly is the Karta subalgebra, by the way? Is a maximal set of operators in your Lie algebra which commute among themselves, right? What does this mean? This means that anything which commutes with all, remember, something which commutes with all the Karta generators must commute with all the Karta elements. Is that okay? The distinction between elements and generators are, of course, basically one between a vector space and a basis. The Karta subalgebra is an entire subalgebra. It's a subspace of the vector space carrying the Lie algebra, and it's also a subalgebra in its own right. Okay, it's a Lie algebra in its own right. Why? Because commutators of HIs, of course, give you something in that space, gives you 0, which of course is in that space. Now, what we are saying is this is specific. Say, if you have any specific E alpha and you take its commutator with E minus alpha, you get another operator, and this operator has to commute with all the HIs. So this must be an element. Is that okay? Because remember, the Karta subalgebra contains everything which commutes among themselves. It's maximal. So anything which commutes with all the HIs must be an element of the Karta subalgebra itself. Is that clear, or does it require further explanation?
No, sir, it's fine.
Okay.
Sure.
So what do you know about it? You know that this must be of the form because the HIs that we talked about, H1, H2, HF, are the generators, which means they're the basis vectors of the Karta subalgebra. You must have this. But I'm using the summation convention, that is, I is summed over 1 to m. Okay, this really means this, although I will not write the sum any longer. That's a generic statement, right? Any element of the Karta subalgebra has to be of this form. But how do you find out beta I? Well, simple. All you have to do is remember we had this Hi Hj was lambda delta Ij, right? Is that okay? Well, lambda was the constant that we use for all normalizations in the adjoint representation specifically. So what I do is just take it should be Hi dagger, but Hi being Hermitian, Hi dagger is the same as Hi. Right? This is the state add E alpha, E minus alpha, on which you apply add Hi, actually add Hi dagger and take the trace. And that gives you beta I. Actually, doesn't give you beta I, that you have to multiply this by 1 by lambda to get beta I.
Sir, the inner product of HI HJ is HI dagger HJ, right? I mean, conjugate. So this one should be HI
But
dagger
Hi
and
dagger, Hi is a Hermitian.
so HI add E alpha E minus alpha. Why did you write add HI instead of HI?
No, that's because, strictly speaking, this is really in the adjoint representation. The operators that who's okay, sorry. I think I made a mistake. Yeah, I did make a mistake. Sorry, I did make a mistake here. You're right. I got myself confused among which state we were in. This is really a generator HI. Yeah, right. This is an HI element. So this really should be. You are perfectly right. It should really be just this. Not the adjoint representation. Yet using the fact that the operators themselves have this normalization. These operators are vectors, right? These vectors have the normalization. And now this is straightforward, right? Okay, let's just check how straightforward this is. We just open this out. You get hi e minus alpha e alpha. Okay, so I can write this second line as e minus alpha hi e alpha. Right? I can do that, right? Cyclicity of trace. And I can write the second term as this. Is that clear to everybody? All I'm doing is taking this, moving it to the front, which I can always do. And here I'm taking this, moving it to the back, which I can always do. And that really is E minus alpha. Okay, there's a 1 by lambda in all of this. So let's put a lambda on this side. E minus alpha. Now this is hi comma E alpha. What does this give you? This is alpha I, right? Is people with me or have I lost everybody?
Yes, sir, we understand.
Trace of E minus alpha. By the way, what is trace of E minus alpha E alpha? That's trace of E alpha dagger E alpha, right? Is that okay?
Yes, sir.
And that's lambda, because that's the normalization we choose for all our vectors, so that's going to be lambda alpha I. What that tells you is ultimately, and this is the important step, tells you that alpha, sorry, E alpha commutator with E minus alpha, not only is it a Karta subalgebra element, a very specific Karta subalgebra element, it has to be alpha dot h, where whatever the root is, that goes here. Okay? And so, notice that if I took alpha dot h, this element, and tried forming this commutator, that will bring out an extra alpha I. Of course, there's a summation of I involved. There's alpha I, E alpha, or right? And alpha dot h with E minus alpha, very similarly, will come out in minus alpha vector square. Okay, since I'm not using the arrow on top of alpha anyway, let's just use this notation. I think it should be easy to understand that when you write alpha mod square, it's a vector whose length you're talking about. Is this okay? So what we find is this. You take these three operators, alpha dot h, E alpha and E minus alpha, they form a closed subalgebra, right? Take any two of them, form a commutator, you get a third one. You get something in that state. You don't get anything else. But this is minus, E minus alpha. Right? So, corresponding to every root vector alpha in your adjoint representation, there is this closed subalgebra formed by alpha dot E alpha, E minus alpha, and alpha dot h. Not only that, this is a 3-element closed subalgebra, and a very familiar 3-element closed subalgebra is this one, J3 J plus minus, and J plus commutator with J minus is how much? SU2 rotations, angular momentum. What is J plus comma J minus?
Two J3.
2J3. However, the 2 depends on your choice of how you define J plus J minus. We define J plus minus as J1 plus minus IJ2, which is something we often do. You get 2J3. But if you define it by this, then this commutation relation doesn't change because you get a 1 by root 2 on both sides. But this commutation relation has a half on this side that cancels out the 2 and you get J3. So that's one of the standard definitions of J plus J minus that is often used with the 1 by root 2 thrown in. Of course, if you want to reconcile this with the other case, you will need to remember that these J plus J minus are really 1 by root 2 times whatever J plus J minus you are used to. So when you say J plus acting on Jm produces something, this J plus acting on Jm will produce 1 by root 2 times that thing. Okay. Well, no real reason why you choose one over the other, except that mathematicians usually like this one more. Well, it makes the factors even easier in the Lie algebra. Of course, notice that to a mathematician, the abstract Lie algebra is more important than the individual states. So the extra factor of root 2 which you get in the definition of the states, that's really less important than the fact that the Lie algebra has a simpler form here. Of course, not a big simplification. You have just a 2 missing. But if you go by that and want to make something similar, notice that alpha dot h e minus alpha gives you alpha mod square times e minus alpha, doesn't give minus. So at least this one, which is there even in our standard quantum mechanics commutators, there are plus minus 1. Here you have plus minus alpha mod square. But that's easily taken care of. Instead of alpha dot h, use this. Let's change colors. Let's make this red. Oops. So this is a definition. You define this. That way E3 comma E plus minus alpha will automatically become my plus minus E plus minus alpha. Okay? So this part of the SU2 computation relations, you are matching up. However, if you did that, E alpha comma E minus alpha will be alpha dot h, whereas you want to get by mod alpha square. Right? Just to make it look exactly like what you had. So what would you need? You need E plus minus to be defined as is that okay? That way, E plus commutative with E minus will essentially have an extra 1 by alpha mod square factor. Right? That will give you alpha dot h by alpha mod square will just be E3. And E3 commutative with E plus minus will be plus minus E plus minus. Exactly what you need. Is this okay with everybody? This is a critical part of the definition. So or strictly speaking, not a root, but a root pair, alpha and minus alpha. This, of course, a closed subalgebra. What we have really realized right now is that this really is an SU2 subalgebra. Okay. So there's one SU2 corresponding to every alpha minus alpha pair. Okay, SU3, for example, has 8 generators. I'm just stating this. There's something which will be described in a lecture by one of you. SU3 has 8 generators, but only 2 Karta generators. That means it has 6 other generators, and those 6 can be combined to form linear eigenstates of adjoint of H1 and adjoint of H2, the two Karta subalgebra generators of SU3. So there will be 6 roots, but really 3 pairs, right? And these 3 pairs correspond to 3 distinct SU2s. And frankly, SU2s are so much easier than any other Lie algebra that you can think about. And once you see that semi-simple Lie algebras can be essentially broken up this way into SU2s, it's obvious that you will be able to derive a lot of the properties of arbitrary semi-simple Lie algebras from what you already know about SU2. So the fact that you learned a lot about SU2 in your quantum mechanics course, simply because there it had this deep connection with rotations and angular momentum, is going to come in very, very handy in all this that we are going to talk about. So the entire structure theory of semi-simple Lie algebras, at least, if you know SU2s, you can sort of work them out. But the important result, every pair of roots, alpha and minus alpha, corresponds to an SU2 subalgebra. Okay, any questions so far?
Sir,
Yeah.
I have to leave. I got something coming up, so I'm sorry.
No, that's okay, because I don't really want to talk about too much today, but there will be a couple of more things. Then we'll continue afterwards. Okay, fine. Anybody else has a question? If not, let's just talk about some of the very important results that we can get out of here. Now, it so happens that because we know a lot about the structure of SU2 Lie algebras, that's actually enough to tell us quite a lot about the structure of our possible roots of a system. In fact, one important thing that we can immediately show is that what that means is, if for a given alpha, you have an E alpha. If you had an E alpha prime, not alpha prime, but E prime alpha, same alpha, but another generator, you can show that E prime alpha and E alpha must be one and the same. You can't have more than one generator corresponding to a given root. Now, remember, the roots are just the eigenvalues, right? So what we are really saying is that in the adjoint representation, the root vectors, these eigenvalues, of course, are degenerate, but they are the degeneracy is completely lifted by specifying all the eigenvalues corresponding to the Karta generators. That is, say in SU2 there are 2 Karta generators. If you specify the 2 roots for a given root vector, that gives you a unique generator. You can't have more than one generator corresponding to that. So that's the result. So how do we get such a result? Because remember, in general, in the general representation, of course, a given weight simply says these are the eigenvalues corresponding to the Karta subalgebra generators, but there may be other, but specifying that may not be sufficient to completely specify which vector you're talking about. That is precisely why we had this notation, remember, mu, d, but there was also this x where the extra labels. Here, what we are saying is basically E alpha, this states E alpha are basically alpha in that notation. Alpha, and you don't even need to specify what the D is because we know it's the adjoint representation. But there are no other labels, which is why E alpha, we wrote it as E alpha, not just ket alpha like this, but that's just a notational thing. But the moment you say alpha, you know which generator you're talking about. Of course, that's a statement. That's not a proven thing right now. So let me just show you how to go about proving this. Well, the proof is by contradiction. You just assume so let's just assume that what I said right now is wrong, that you can have two generators. Of course, when you say two generators, E alpha and 3 times E alpha doesn't count, right? Any multiple of an eigenvector is always an eigenvector. So you're saying there are two independent generators corresponding to the same root, alpha. And because they're independent, you can even if they were not orthogonal to begin with, you can always orthogonalize them and choose them in such a way that you get 0 for this. Or so we have chosen this E alpha and E prime alpha in such a way that the trace of E minus alpha, E prime alpha is 0. Now, let's take the inner product of Hi with E minus alpha, E alpha prime. It's commutated. Remember, this is an element of the Lie algebra. This is also an element of the Lie algebra, and the inner product that we are talking about is basically trace E minus alpha. My handwriting should be better here. Well, sorry, what I will do is I will do something slightly different. Okay, let me just okay, is everybody with me so far, or has everybody gone to sleep?
No, sir. Yeah.
Okay, more importantly, I am still here. Okay. So let's do one thing. Let's just change the color a bit so that it's easily visible. We will take a look at this operator E minus alpha, which remember is E minus alpha. When you say E minus, this is by definition E minus alpha by mod alpha. Okay. So just take a look at this. Same thing as what we did a while ago, except that what we wanted to look at is use the properties of E minus. E minus I already know is an SU2 generator. Now I will let you figure out that because of the cyclicity of trace, this essentially becomes the same, not essentially, this exactly becomes the same as this. And just use the cyclicity of trace to rewrite. Remember, this is already a trace. This is trace of lambda times trace of hi e minus e alpha prime, then just use the property of cyclicity of trace, open up the commutator if you have to, and just rewrite this. I can show that it becomes this. But then this simply becomes minus alpha I lambda. So this hi e alpha prime. Remember, e alpha prime is an eigenvector corresponding to the same eigenvalue of add hi. So hi commutator with alpha prime gives you alpha I out. But this is 0, right? Because we have already assumed that this is 0. We have assumed that we have already orthogonalized them. Okay?
Sir, I think these are the same steps as done a little while ago while proving the commutator of E alpha and E minus alpha.
Almost the same. So, yeah. These are nothing new. This is just a slightly different thing that we are looking at. This is similar, except that there is a difference. Remember, there we said E minus alpha and E alpha. We are trying to show that there is, once you have got this E alpha, the same step, because ultimately it depends only on the commutator. So ultimately the results come out to be the same. But we are just assuming that in addition to the E alpha, you also have an E alpha prime, which has the same eigenvalues. Of course, because only the commutator is important, you get the same result. But remember, this is a different thing. There's a prime here. Okay?
So shouldn't that be alpha I prime? Like minus alpha I prime lambda trace of E minus
No.
E alpha
No,
prime.
no. I think you're I prime, alpha I prime would have meant that this is a different root altogether. Remember, what are we trying to say? We are trying to say that corresponding to a given root, for a particular root vector, there is a unique generator. That is, we started by assuming the prime, that's why the prime is not on the alpha. These are not two different alphas. Same alpha, two different generators. We are going to prove that that's not possible. Okay?
Yes, sir.
But in order to prove that, we start by saying, okay, same alpha, but two different generators. Let's start with that. And because they are two independent generators, I can always orthogonalize them. I can start with this. And then you end up with this result. So it's not exactly the same as the one we did before. So this thing, what does it tell you about E minus E alpha prime? This operator is orthogonal to every one of the HIs, right?
It's a linear combination of no.
But first of all, it corresponds. By the way, what weight does this? What root does this correspond to? E minus E alpha prime essentially is proportional. This is essentially the same thing, apart from a factor, as E minus alpha E alpha prime. Right? So what's the weight corresponding to this? Or what's the root in particular, because we're in the adjoint representation? Yeah, quickly. You already did this. This is something we did already. What was the root corresponding to E minus alpha comma E alpha? This is what we did just a while ago.
It came out to be alpha dot H.
No, this did not come out to be alpha dot H. This is alpha. This came out to be alpha dot H, but that's not okay. Sorry, that's exactly what it came out to be. However, my question was, what is the root corresponding to this? That is to say, we're going to apply HI, adjoint HI on this. That is, take the commutator with HI of this quantity. What would I get?
0.
We would get 0. In fact, that is exactly how we decided that this quantity has to be of the form beta I HI, because it's a Karta subalgebra element. Okay? And then when we wanted to prove that beta I has to be equal to alpha I. So that's why we ended up with the result that this is alpha dot h. But for that, what we first showed that this thing has a root of 0. Now, why does it have a root of 0? Simply because this shifts, right? Add E minus alpha, acting on E alpha, just shifts the root alpha by minus alpha and gives you 0. That's it. But the same thing will happen here. Remember, this alpha and E minus have the same. E minus is basically E minus alpha. Okay, and E alpha prime may be a different root, different generator, but has the same root. So this must be of root 0. This commutator must have root 0. That means the commutator must be a member of the Karta subalgebra, right? Same argument as here. Is this clear? Maybe it will be easier to if you thought of it this way. If you took two different roots alpha and beta and formed E alpha comma E beta and tried taking HI commutator with that, you will see very simply, you just use Jacobi identity. This is one of the exercises in Georgia, but this is a trivial exercise. It comes out with this. This is just a consequence of the Jacobi identity. So what does it tell you? It tells you that if you take any two roots, generators corresponding to any two roots, form the commutator, you are going to get a root alpha plus beta. Okay. There's a catch. It might so happen that alpha plus beta may not be a root, in which case then the only conclusion you could draw is that this must be 0. Exactly the same thing that we did with standard raising lowering operators. You got new eigenvectors, but if the only way you could possibly not get an eigenvector is by claiming that when you did this shifting, you ended up with 0. So either E alpha comma E beta, the commutator will be 0, or it will correspond to a root alpha plus beta. So since E minus corresponds to minus alpha and E prime alpha by assumption corresponds to plus alpha, this corresponds to a root 0, minus alpha plus alpha, right? So everything which corresponds to a root 0 must commute with all the Karta generators, which means it must be a member of the Karta subalgebra. But what have we proven right now in this step? Yes? What have we proven? What is this? This is the inner product with the ith Karta generator of this operator. That's 0. What does it tell you? Let me just quickly recapitulate what I am saying. I am saying E minus E alpha prime, because it's proportional up to a factor, is just E minus alpha E alpha prime, must have weight equal to 0, so must belong to Karta subalgebra. That's my statement 1. Is everybody okay with this?
And then you showed that it's perpendicular with like
then we showed
inner
that
product is
HI,
below.
inner product with E minus E alpha prime for all the Karta subalgebra generators is 0. So what does it tell you about this? A Karta subalgebra element which is orthogonal to all the basis vectors of the Karta subalgebra, what can it be? Okay.
0.
Yeah, it's obvious it has to be 0, right? The only vector in a subspace which is orthogonal to all the basis vectors is 0. Nothing else is. There are two steps to it. One is this alone would have shown you that this operator is orthogonal to all the Karta subalgebra elements. what that would have meant is that it's orthogonal to the Karzai subalgebra. It could be a non-zero vector, non-zero operator, but which will have no component in the Karzai subalgebra itself. Whereas the being weight zero, it has to be a Karzai subalgebra element. If you put them together, the only possible conclusion you can draw is that this operator must be zero. Right? That is, E minus must commute with the alpha prime. No problem with that. That alone is not an issue at all. E minus corresponds to E alpha prime. Why is that a problem? All we are saying is E alpha is one generator corresponding to root alpha, E prime alpha is another. All we have shown is if you use the lowering operator E minus corresponding to this E alpha, that must commute with E prime alpha. That in itself is nothing wrong. That can always happen. But if you take this, remember E3 is alpha dot H by alpha mod square. E alpha prime. Okay, E prime alpha. This, keep the name straight. So what is this going to give you? This is alpha I by alpha mod square, length squared, HI E prime alpha. What is HI E prime alpha? Come on. What is this?
And alpha is just going to come out.
Alpha I is going to come out.
Yes.
Right? And that alpha is going to cancel this one. That is alpha is going to be alpha I. The sum over I, of course. Alpha is going to be alpha mod square. So that cancels this one. So we get E prime alpha. So add E minus acting on E prime alpha is 0. Add E3 acting on E prime alpha is E prime alpha. So can anybody see that there is a problem with this? If this happens, there's something which goes very wrong. According to what we already know about, so this right. Can you see that there is something which goes very wrong here, according to whatever basic ideas you remember? Add E minus, the adjoints obey the same Lie algebra as the original steps, right? That means, oops. Or basically, all you are saying is they form a SU2 subalgebra, right? So all you are saying is E alpha prime is a simultaneous eigenstate of a SU2 lowering operator with eigenvalue 0. It's killed by SU2 lowering operator, and it's an E3 eigenvalue. It has an E3 eigenvalue of +1. Can you see any contradiction here?
It should have gone to -1 when acted by EY minus.
Okay, close. Okay, what do you know about SU2 Lie algebra? SU2, if you have an SU2 representation, then you will have a lowest weight state, which is killed by E minus, the lowering operator. No problem there. So this just shows that E alpha prime must be the lowest weight state in an SU2 representation. However, what do you know about the E3 eigenvalue of a lowest weight state? The SU2 representations are labeled by a label J, right? The representations labeled by J, individual states within the representation are labeled by M. Okay? And what does M range over? When you say Jm, that's the notation that we are used to, but if you think in terms of individual representations or individual irreps of SU2, the J is the same for all the states, right? So J essentially labels the representation. The M changes from state to state, and the M is what labels the individual states within the representation. So what is the M corresponding to the lowest weight state? The one which is killed by E
It
minus.
should be minus J.
Right. And here what we are seeing is the M corresponding to E alpha prime is +1. That's impossible. Minus J can be what? Can be 0 or can be a negative number, can never be +1. So this thing is a contradiction to what you already know about the properties of this of the SU2 algebra that you know. SU2 algebra, you already know all its representations, you know what properties it has. You know in particular that you will have a lowest weight state which will be killed by E minus, the lowering operator. So we don't flinch when we see something like this. Neither do we flinch when we see something like this separately, because E3 definitely can have +1 as an eigenvalue. We know that. But we know that you cannot have both of them together. You cannot have a state which has +1 eigenvalue killed by a state, by the lowering operator. Is it okay? Is that clear?
Yes, sir.
Well, actually, you could argue that, okay, why not? All you would say is, why? Then you apply add E plus on this, you get new N and newer generators with higher and higher eigenvalues. But then you can easily show that you will, that's such a state which starts with at +1 as the lowest weight will never terminate. That ladder will never come to an end, and as a result, you will end up getting an infinitely huge number of generators, which is impossible because these have only finite number of generators here, right? So basically,
So, but add E minus E alpha prime. Why are you saying that that does not make you flinch? Because
well,
we
because
just
it's a lowering operator, right? Lowering operator. This is all you are saying is the lowering operator is an eigenvector with eigenvalue 0, and the lowering operators in SU2 of course have eigenvalue
yes,
0, right?
yes, okay.
The lowest weight state has eigenvalue 0. It gets killed when you apply with that. That alone is fine. Add E3 acting on E alpha prime gives you 1 as an eigenvalue. Fine, I know that E3 can have 1 as an eigenvalue. But you can't have both for the same eigenvector. The same state cannot be both killed by the lowering operator and return an eigenvalue which is positive. Is that okay with everybody? This is just standard SU2. Remember, after this, whatever we will say are basically properties of SU2. We are not actually using anything else. Clear?
So,
Yeah.
say instead of taking adjoint E minus E alpha prime, say we take E plus.
Why? Of course, you can do that, but that will not give that may not give you a contradiction. Okay, I didn't try that, but I think it will not give you a contradiction. But what's your problem then?
I mean, then say
Then you don't get a contradiction, right? Fine. But remember, just because you don't get a contradiction using E plus does not mean that wishes away this contradiction.
no, I thought we haven't fully, but say we get adjoint E plus E alpha prime equals to 0, then we can say right
Then this is fine. Then this doesn't give you a contradiction. As I'm saying, if it were in E plus, then you are saying that this is the highest weight state of a thing, and having a positive eigenvalue for E3 for that state is not a contradiction.
okay.
Okay. But I'm not worried about that. Remember, the thing has to be self-consistent, right? You cannot, just because one way of looking at it doesn't give you a contradiction, doesn't mean it's okay. It cannot have a contradiction any which way you look at it.
Yes, sir.
Is my point clear?
Yes, sir.
Because that's how proof by contradiction works. You look at the one which gives you a contradiction. Of course, there may be other arguments which will not give rise to a contradiction. But that doesn't make the whole thing legitimate. If you have one way of producing a contradiction, that means that there is a problem with what you started out with. And here the assumption you started out with is corresponding to an eigenvector alpha, the root vector alpha, there are two different generators, E alpha and E alpha prime. That cannot happen according to this. Is that okay? Now, I fully give you that there may be 20 other things that will not give a contradiction, but that's not how contradiction, proof by contradiction works. Proof by contradiction essentially works by starting with an assumption which you want to disprove and show that that leads to a contradiction. Doesn't mean that it will lead to everything being contradictory. Okay? Have I made myself clear? Suppose you say something like you want to prove that all numbers are prime. You start with that. Okay. I'm pretty sure you can think of many things that you will get. Say, you add these two integers, you get a positive integer. Add two primes, you get a positive prime. Is that a contradiction? The answer is no. But fine, that's not a contradiction. But if you assume that all numbers are prime, there are plenty of ways of landing up with a contradiction. And the moment you have one way which lands you in a contradiction, that means that you have a problem. That means something you assumed was wrong. Okay. So, just to summarize, what we have proven is E alpha is uniquely specified by alpha. This is a property of the adjoint representation. In a general representation, it's possible that a particular weight might be degenerate, in fact would be degenerate, would have multiple states corresponding to that particular weight. But in the adjoint representation, you have no degeneracy in this sense. Once you specify the entire root vector, the generator is uniquely specified. This is a property which, again, this just to remind you, where did this come from? This came from what we already know about SU2. We didn't have to learn or use anything else. Okay.
Sir, this basically boils down to the statement that you made that each root pair corresponds to a SU2 algebra, subalgebra.
Yeah, but no, not really. Each root pair corresponds to an SU2 subalgebra. All you're saying is that this is unique. We didn't say that. Now we are saying that.
Oh, okay. Yes, yes. By the contradiction.
Yeah, because if you had a E alpha prime which had the same alpha, then E alpha prime, E minus alpha prime would have given you another SU2.
Okay.
Now, this is another immediate consequence which you get, which is this: if alpha is the root, then no non-zero multiple of alpha except minus alpha, which we already know is a root, okay. So we already know that alpha is a root. That means we already have an E3, E plus, E minus corresponding to alpha. Okay. The fact that you have an SU2 corresponding to alpha immediately tells you that any multiple of alpha, apart from E minus alpha, apart from minus alpha, can be a root. How do you prove that? Well, again, go by contradiction. You assume that there's a K alpha. So E3 acting on Ek alpha, which is commutator of E3 with Ek alpha, of course. What will this be? What will this be? Well, this will correspond to the commutator which is again alpha I by alpha square hi Ek alpha. So what is this going to be?
K into Ek alpha.
Right, because it's going to just take this K out. This is going to take K alpha I out, and alpha is by mod alpha square will cancel, and you just get K Ek alpha. So what does it tell you? It tells you that E3 acting on Ek alpha is basically K times Ek alpha. So what does it tell you about the possible values of K?
Plus minus 1.
No. Why?
No.
No, that would be the answer. That's what we want to prove, that the only possible values of K are plus minus 1. But if all we have seen is E3 acting on Ek alpha, so this is, remember, an SU2 operator, SU2 E3 operator. E3, remember, is J3 basically. And there is an eigenvector to that, right? Corresponding to eigenvalue K. What do you know about the eigenvalues of SU2 SU2 E3? Come on. This is quantum mechanics, you know this. What are the possible eigenvalues of E3?
Minus J to J. So
okay, what in general, what is an possible eigenvalue? What tells you that K can be an eigenvalue, and what tells you it cannot be? Simple question. You know the answer to this, by the way. You actually gave me the answer to this, but just suppose I told you K is 7.25. Would you agree? Is it possible?
It should be either integer or half integer.
Okay, exactly. You already know this, right? All the possible eigenvalues of E3 are integer or half integer, or to more precise, should be half integer. Half integer covers everything, right? Half integer covers both integer and half integer. You do agree with that, right?
Yes.
Okay. So I already see that K cannot be any value because of the fact that alpha exists. Alpha is already a root, and hence this SU2 subalgebra exists. This immediately tells me that K cannot be anything, can only be integer or half integer, or as you said, or half integer. Okay. Then that's the first step. The next step is to show that will force us to say that the only possible values of K are plus minus 1, which of course is not obvious at this stage, right? At this stage, all we know is K can be any integer or half integer. But then, let's say if K is an integer, there are two possibilities. It's an integer or odd half integer. Sorry, not odd half integer, half odd integer. If K is an integer, then because you have a lowering and raising possibility here, if K is negative, suppose K is neither plus 1 or minus 1. It's an integer. What can it be? It can be 5. Then I can apply E minus 4 times, and I will get a state with E3 eigenvalue 1, won't I? Yes or no?
Yes.
Okay. With minus 5, I could hit it with E plus. 4 times I will get minus 1, 6 times I will get E plus 1. Anyway, but do I already have an plus 1 eigenvalues thing with E3?
Yes, and that is unique.
That's E plus, right? We already have that. And this E plus cannot be what I get by hitting, say I had E5, hit it with E minus 4 times, I get something. This something has to be unique, but this cannot be this E plus that we had. Why? Because E plus, hitting E plus, what will that give you? Come on. Remember, when I say E plus hitting the state E plus is the same thing as a commutator of E plus with E plus. What is that?
0.
Right? So, of course, E plus, notice that E plus, E minus, and E3 actually give us a representation of the SU2. Not only are the generators of SU2, they also give you a representation of SU2, right? They give you the spin 1 representation of SU2, which, by the way, you already should know. That angular momentum operators are vectors, right? Vectors under rotation. That means they behave like all vectors under rotation. They give you a spin 1 representation. And you can immediately see that E3 acting on E plus is what? Plus E plus. E3 acting on E minus is minus E minus. E3 acting on E3 is 0. 3 states, 1, 0, minus 1 eigenvalues. Killed respectively. E plus is killed by E plus. E minus is killed by E minus. All that. That again is nothing new. This is something which is there already in quantum mechanics that you learned. But what you see is if k is an integer, any integer other than plus 1, not integer greater than plus 1, let's say, then this will give us, you will find a state by hitting with E minus sufficient number of times, so I'm not giving this blank, so that you will get an E3 eigenstate corresponding to eigenvalue plus 1, which will contradict the uniqueness that we just talked about. So you cannot have an integer k in the story.
Sir, did you just say that the adjoint representation of ACO2 is the same as the spin 1 representation?
Yeah, it is. Has to be, right? Because it has to be a representation, right? All the spin values. And here that's sort of trivial, isn't it? Because how many elements does the adjoint representation of SU2 have? How many independent elements? What is its dimension?
Oh, it's 3, so it must
And every
be.
SU2 representation is characterized uniquely by its size. There's only one representation per size. End of story. The spin 1 representation has 3 elements, and that's the only one which has 3 elements. That shouldn't come as a surprise. That's something which you already know, by the way.
Didn't
The
notice
adjoint
this.
representation cannot be something which falls from the sky. It's one of the irreps that you have here. That's it. Now, what we have just proven is that k cannot be a positive integer. Cannot be a positive integer. By the same argument, you can show it can be a negative integer. What prevents k from being a half integer? Say 7 by 2. Okay, let me give you a hint. If you start with 7 by 2, hit with E minus 3 times, what do you get?
Half.
Once again, you get?
Minus.
True. Okay, but you don't, this does not give you a contradiction apparently. Right? Well, it does. Can you see how?
Maybe we can scale the vector and define a new vector.
Not really. You can't scale eigenvalues. Right? Scaling eigenvectors does not scale eigenvalues. But you're close. So I mean 7 by 2 alpha, here it's half alpha minus half alpha. Okay, let's call half alpha alpha prime. Okay, let's not, this is alpha prime, a new alpha, which is half alpha. So what are you saying? You are saying alpha prime, this is a root which exists, okay, right? And why is that a contradiction? Because then you are saying alpha, which is twice alpha prime, is also a root. Don't you see that a while ago we proved that if you have a root, any integer multiple of that cannot be a root? That's what we just proved, right? What we proved here is if you have a root, any integer multiple cannot be a root. Now that left open the possibility of a half odd integer multiple. But if you have a half odd integer multiple, then you will have half alpha. Fine, that's a root, not a problem. But if that is a root, then alpha cannot be a root. So because we started by assuming that alpha is a root, 7/2 alpha or any half integer value is out. Okay. So a multiple of a root cannot be a root. Okay. Okay, if you give me 10 minutes, I will just end with one interesting result. Is anybody in a hurry to leave somewhere after this? I know it's been long and you could have gone to sleep by now, but still. Is it okay if I take 10 minutes or do you want me to wrap it up now?
No, it's okay, sir.
Okay, fine.
It's okay.
Let it be on your heads then. Okay, let me just remind you that my E3 is alpha dot H alpha mod square alpha 1 H1 plus alpha 2 H2 and so on. And now let's go to an arbitrary representation. Any representation, of course, that includes the regular representation or the adjoint representation as a part of it. But this is a statement which I'm making about an arbitrary representation. Okay, let's simplify notation a bit. Let me just drop the X. Okay, we might even drop the D. Okay, anyway, at least let's keep the D on just to show that this works for an arbitrary representation, not necessarily the adjoined one. Now, what is E3 when it acts on mu D? Remember, when I say E3 acting on mu comma D, I mean the generator corresponding to this particular Lie algebra element. This is a Lie algebra element, right? Alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3 by alpha 1 square plus alpha 2 square plus alpha 3 square. This is really, the alphas are just numbers. So these are linear combination of Lie algebra elements. This is a Lie algebra element. Corresponding to that, there's a generator. So like all good phrases, we are not notationally cluttering things up. We are using the same notation for the generator, for the operator corresponding to a particular Lie algebra element and the Lie algebra element itself. So this E3 acting on mu comma D, what will it give you? So E3 is simply, remember, alpha dot H so what does alpha dot H is alpha 1, these are just numbers, alpha i's. Hi is the operator. What does Hi give you acting on mu? There's a definition, remember, how did we define these mu comma D's? These are the eigenvectors corresponding to the generator's Hi. Simultaneous eigenvectors with eigenvalues mu I. These are the weights. You remember this, right? This is what we started with. Since you can simultaneously diagonalize all the HIs, you can find the simultaneous eigenvectors, and this is what you are going to get. And what is this going to give you? So now I'm essentially exploiting the E3, E plus, E minus generators that we have, operators that we have. Well, these are operators which are which correspond to the origin, the E3 plus E minus that we talked about so far, but they will have the same algebra, so they will behave the same way. So E3 corresponds to an eigenvalue alpha dot mu by alpha mod square. So what do you know about alpha dot mu by alpha mod square now? Remember, alpha are your weights, or alpha are your roots, and mu is an arbitrary weight in any arbitrary representation. What does this tell you about alpha dot mu by alpha mod square? This is just a number, but what, is there any restriction on this? Come on. E3. Shouldn't that be a big giveaway? This E3 operator may not be the same E3 operator as that one, but it definitely has the same commutation relations. E plus E minus commutator is E3 and so on. And E3 if you remember anything about your SU2 representations, what went into the derivation of the SU2 representations, the possible eigenvalues and all that? All that we used in quantum mechanics, did we use the specific nature of the representations? That is, what the specific form of the operator looked like? Did we use that? When we found out the representation theory for the SU2 generators. In other words, let me just remind you of what we did. We did J3JM J plus minus JM was the 1 by root 2 simply because of the definition that we have changed and so on. And M or twice M belongs to integers. In all of this, in deriving all of this, did we need to use a specific form of J3, J plus, J minus? Or what did we really need?
So we
Yes?
did use J plus equal to J1 plus IJ2.
Yeah, but J1 plus IJ2 is not a specific form. You're just using a specific combination of the operators. But J1, J2, did you use what form J1, J2 have?
J1, J2's form in terms of?
Now, let's say, did you have to use something like, say, H cross by I x del del y minus y del del x? Let's say. That's J3, of course. L3. You have to use that to derive these results. How did you derive these results? That's my question anyway. You started by assuming that J3 has some eigenstates, right? And then what did you use? You started with this three commutation relations, right? The Lie algebra. Then what did you do? Then you said, okay, we can combine J1, J2 to form this. That's just a change of basis. In fact, that's diagonalizing J3 at J3. You have found out eigenvectors of at J3 by combining J1, J2 together. But in all of this, the only algebra that you used was the algebra of commutators, right? Then you argued that, okay, because of this particular commutation relation, J plus is going to raise the J3 eigenvalues, J minus is going to lower J3 eigenvalues. And if you want a finite dimensional representation, you must stop somewhere, both the raising and the lowering. And that gives rise to all these statements that twice M must be an integer, say twice J must be an integer, and then M must differ from J only in steps of unity and so on. This is just ordinary quantum mechanics. We didn't do anything else. My point is this: everything here depends only on the commutation relations, nothing else. I don't care where the operators come from. If I have operators, three operators, E3, E plus, E minus, which obeys the same commutation relations as J3, J plus, J minus, the statements you are making about the nature of the eigenvalues of E3, E plus, E minus will stand. Doesn't matter what E3, E plus, E minus came from. Is that okay with everybody? When you did quantum mechanics, didn't you derive these results?
Yes, sir. It's okay, sir. Derive it using the commutation relations of.
You just use the commutation relations, nothing else. Of course, you did use something else. You used the fact, I guess. So J square equals J1 square plus J2 square plus J3 square and so on. And then you use the fact that there should be an upper bound. For a given value of J, there should be an upper bound on M to show that there's an upper bound and upper cutoff and lower cutoff. But the same argument can be made without using J square at all. All you would have to say is, okay, I am only looking for finite dimensional representations. If you're doing that, this raising and lowering must stop. That's all you really need. So what does it tell you about alpha dot mu by alpha mod square? This is the eigenvalue of E3. E3 is an SU2 generator. E3, E plus, E minus obeys the same commutation relations as J3, J plus, J minus. So what do you know about this quantity? Then E3 eigenvalue, what do you know about E3 eigenvalues? Or J3 eigenvalues? Come on. Just now you told me that the eigenvalues depend essentially only on the commutator. So the commutators are the same. So what can an eigenvalue for E3 be? You have already used this before. So I'm not asking you for its value. You can't tell me that, but you can tell me something about it. Come on. SU2 generator, eigenvalues, what are the possible values? I guess since you have given the answer before, you might be hesitant to say that again. Because that's the only possible explanation I can find for the silence. That or I've been disconnected.
No, sir. I don't understand. Like AC2 for AC2 generator it goes from
No,
so all of
goes
them.
from is unimportant.
Minus.
What are the possible values? Can 1.25 be a value? Can 1.37 be an eigenvalue for AC2 generator? When you say goes from, you're talking about a particular J. For a given J, where does it go from? Forget the J. But is it possible to have 1.37 as an eigenvalue for an AC2 generator?
So it's like it belongs between -1 and 1.
No.
Because,
Come on. -1 and 1.
so E3 acting on it's acting on mu and D. So
Yeah, so this is not the same representation as before. Any arbitrary representation. This is an arbitrary representation. E3 acts on a state. So mu comma D are simultaneous eigenstates of all the HIs corresponding to the mu I weights. We take a particular combination of HIs, namely E3, corresponding to the root alpha, and we form alpha dot H by, and we get alpha dot mu by alpha mod square as the eigenvalue. for E3. So these states which are simultaneous eigenstates of HIs are eigenstates of E3 with eigenvalue this. So what do you know about the eigenvalue? Okay, what do you know about this? And remember, I have changed the equal to a belongs to so that it's easier for you to answer the question. Twice an E3 eigenvalue, what can you say about that? I thought this is a trivial question. And it is. By the way, you may be overthinking this. All I meant is this. Come on. Is that okay with everybody? Or is there a confusion about this?
Yes, sir, I'm confused. I'm a bit confused.
Look, E3 is an operator, right? E3, E plus, E minus has a definite commutation relation. And that commutation relation immediately tells you that in any finite dimensional vector space, only possible E3 eigenvalues are half integers. Why? Because, well, E plus is going to raise the E3 eigenvalue. You agree?
Yes.
E minus is going to lower it. Again. So unless E plus and E minus were both the action of E plus and E minus both ended, you're going to get an infinite number of states.
Yes.
Okay, so if you start with a given eigenvector for E3 and kept on hitting with E plus, things must end somewhere. Okay. And if you
Yes.
started with the same one and he kept on hitting with E minus, the things must end somewhere. Now, what is the difference between the two eigenvalues in this case, the highest one and the lowest one? Okay, again, when I say what is, maybe the specific adjective, what is maybe throwing you a bit. What I mean really is what are the possible values for the highest and lowest weight?
Well, as
You
soon
can
as
show from the algebra that these two have to be negatives of each other, right?
yes.
Because
So
and because the gap therefore is whatever, if the highest weight is j, the lowest weight is minus j, the gap is 2j. And because you have to be able to go from one to the other by changing in value, eigenvalue of 1, this 2j must be an integer. This is quantum mechanics for angular momentum, nothing else. 2j must be an integer because unless 2j is an integer, you will not be able to go from minus j to plus j by raising or lowering. And say if 2j were not an integer, then what would happen? Say j was 1.2. Then you will have a state with 1.2. J here is not the j square eigenvalue, it's just the highest eigenvalue for E3. Suppose you are 1.2. Then you hit with E minus, then E plus kills it, fine. But hit with the E minus, what will happen is you get 0.2, then you get minus 0.8, then you get minus 1.8, then you get minus 2.8, and there's no ending. The thing never ends. Because you can show that if that is
So
E plus, yeah.
Alpha dot mu by mod alpha square is the analogy to J here.
No, it's not an analogy at all. E3 is the analogy. Okay. Alpha dot mu by alpha mod square is not analogous. It is not J, but M.
Yeah, it's M, and like, so what basically.
Because look, j is the highest possible value of m, minus j is the lowest possible value of m in a finite dimensional representation, and you should be able to go from plus j to minus j in integer number of steps, which means 2j must be integer.
Yeah, so
This is
that's what.
not new, this is quantum mechanics. And that means that any m value has to be somewhere in that ladder of between j and minus j, right? So you should be able to reach that by hitting the highest weight state with e minus sufficient number of times or e plus sufficient number of times, or hitting the lowest weight state with e plus sufficient number of times. What that means is that any possible eigenvalue of E3 has to be either integer or half integer, no other possibilities.
Yes, so that's why once you multiply with 2, it gives you
Or once
the.
you multiply by 2, it has to be an integer.
Ah, right, okay.
Okay, so now notice that that actually puts a huge amount of restriction on the mu's. Remember, we are talking about arbitrary representation, any representation whatsoever, right? So it might look like you can have arbitrary mu values, but you can't. Because mu's must obey alpha dot mu by mod alpha square must be twice that, must be an integer. And that has to be true for all the root vectors. Give me any root vector, you have an E3, E plus, E minus corresponding to that. Using that, you immediately get any arbitrary weight must have a dot product with alpha. These are all vectors in the m-dimensional vector space of roots and weights, so their dot product is fine. That alpha dot mu by alpha mod square must specifically be a half integer. That's a huge restriction to put on the possible states. To get that.
Yes,
In other
so
words,
to be half integer multiple of alpha.
that means you can't just write down an arbitrary vector mu and claim that, okay, I will find some representation in which this vector will be the eigenvectors for all the components of this vector will be eigenvectors for all the HIs. Not possible. Only certain vectors can fit this, others can't. Okay. Notice that all we are using is the SU2 subalgebra that we found for a corresponding alpha, and that's what is telling us this, that you can't have anything. You can have only certain things. Well, it actually gets better. We just use, so far all we have used is E3, right? We saw that E3 acting on mu d is going to be alpha dot mu by alpha square mu d. That told you that mu vector cannot have arbitrary components. The mu vector has to obey this, the twice alpha dot mu by alpha square has to be an integer. That's one very important restriction. But actually you get way more. Why? Because you know a lot about SU2 representations. You know that if you do this, what will you get? This is an E3 eigenstate, right? Mu d is an E3 eigenstate corresponding to this eigenvalue. What will this be? Come on, again, quantum mechanics, theory of angular momentum, nothing more. If you have an E3 eigen, just for E3 think J3. E plus think J plus. Same algebra, so it doesn't matter where it came from.
So E3 acting on this will give you alpha dot mu by alpha square plus 1. And
Right.
mu is a vector. I don't know how mu will exactly change.
We don't have to. The point is, you don't even need to. That's a complicated question. We are not going to get into that right now. We can answer that in the long run. But what we really want to talk about is this. E plus application of that will increase the E3 eigenvalues. That's all we really need right now. Okay? You know what E plus will do, by the way, to mu. Why? Because you know what E plus is. What is E plus? Remember, E plus is E alpha by mod alpha. Right? So what does E alpha do to mu? It will increase mu to mu plus alpha. We did this before. You want to figure out what E alpha. Remember, how do you figure out what this state is? You just ask what HI does to them. What does HI do to this? To figure that out, you have to take the commutator. Why do you have to take the commutator? Because you don't know what HI does to this, but you do know what HI does to the mu D.
Mu plus alpha.
That gives you mu plus alpha I mu D. That's what we started with, right? E alpha shift. And E plus is basically E alpha. It's just a scaled version. Scale is just to fit the standard SU2 commutation relation, nothing else. Okay, so E plus will give you mu plus alpha as for weight. But what is important is this. That is, there must exist whole numbers, that is 0, 1, 2, non-negative integer. There must exist a non-negative integer such that you agree? In other words, E3 is an eigenvalue, right? You hit with E plus, you are going to get a new weight, mu plus alpha. Hit it with E plus again, you get mu plus 2 alpha. Hit it with mu plus again, you get mu plus 3 alpha, and so on. But this cannot continue forever. This must stop somewhere. Okay? Clear?
Yes.
Which means that if you start with an arbitrary weight mu plus p alpha, this thing should be the highest weight state, right? You take this. That is the corresponding eigenvalue for the highest weight state, E3 eigenvalue. This has to be plus j for some j. Is it okay? Highest weight, some j, some order. So, and this is really alpha. For any arbitrary weight alpha, you must have this. There must be some non-negative integer, could be 0. You may already be sitting at the highest weight state, which means hit with E plus 1, you get killed. But if you're not sitting, wherever you are sitting, you will be able to find this relation, right? Is that okay? And there should be another whole number, non-negative integer q, such that is that okay? You realize where this comes from?
The lower bound.
You basically take mu d, keep on hitting with it with E minus. All you're saying is, okay, there must be an end to this. There must be, you should be able to hit with q minus, E minus q times. We'll still get something non-zero, so we'll still get a state. Hit it with q plus 1, hit it with E minus q plus 1 times, you get 0. Okay, so mu minus q alpha will be the corresponding lowest weight state, and that will give you this. Is this okay? This is the critical step actually. This is the really crucial thing that we are doing here. Given any weight mu and a specific root alpha, and this works for all roots by the way, there must be integers, non-negative integers p and q such that minus q is equal to minus j. Of course, given for a given weight or a given root, this p and q and j may differ, but this will work. For a given, if you change alpha, change mu, p and q will change, but no matter what alpha, what mu you take, there will be some positive integer p or non-negative integer p, some non-negative integer q, such that this always works. And so one immediate consequence of this is, if you add them together, you immediately get, cannot be any value, has to be Of course, that doesn't seem like a big thing to say because we already showed that this has to be a half integer. But this half integer has a specific meaning. Starting from a weight, there's only so many times you can shift it along alpha, and so many times you can shift it along minus alpha. And the number of times you can shift, these are p's and q's. So this half integer value is related to the p minus q. Is it okay with everybody? That is, if I'm working in say SU3, this is my, this is say this is a particular alpha, and let's just say this one here is a weight. Then I should be able to shift it parallel to this some number of times, along it some number of times, maybe thrice along this, 4 times along this. But this, if it's 3 and 4, then minus half, that will be the value of alpha dot mu by alpha mod square for this. Okay. Now this in itself is not a big deal because all you are saying is you already knew this is a half integer. You are relating this half integer with how many times you can raise or lower it. Okay. However, it doesn't tell you how many times you can raise or lower it because it gives you p minus q. It just gives the difference between the number of times you can raise it and number of times you can lower it. Strictly speaking, raising or lowering is wrong right now because in a multidimensional vector space, there is necessarily no positive thing. So I'm just colloquially saying raise and lower. Because e plus e minus, of course, are raising, lowering. Now, this is for which representation is this true? This statement? That alpha dot mu by alpha mod square has to be minus half p minus q. Yes?
The entire procedure was followed using SU2.
No, we were using SU2 made out of this. For any representation, you could get E3 plus minus generators just by taking whatever the E3 plus minus were in your original Lie algebra, taking the corresponding operators here because the corresponding operators will obey the same commutation relation. So this procedure actually works for every representation. Of course, the alphas were specifically the roots, which were eigenvalues in the adjoint representation, but mu's are weights which are eigenvalues in any representation. Okay? But this actually becomes even more interesting if you apply it to the adjoint representation. You go back to the adjoint representation and just use 2 roots because there the weights are the roots, right? Then you get something like this, alpha dot beta by alpha mod square. Okay? But you should realize that you used alpha as a root and beta as a weight here. But because you're in the adjoint representation, the weights are also roots. So you can just use the other argument. Use this. What will this be? In other words, how did you arrive at this? You started with E beta, essentially hit this with E alpha, E minus alpha, and
Minus
alpha.
minus p.
Really?
Minus half q minus p.
No, not really. What does this tell you? It tells you that if you start with the root beta and shift it along alpha, how many times can you shift? Okay. And this says start with the root alpha, shift it along beta, a different direction altogether. How many times can you shift? The answer is there is no connection between the two. But the only connection is that this is minus half times p minus q, where p is the number of positive shifts here, q is the number of lowerings. This is minus half p prime minus q prime. Okay, where p prime and q prime are those integers. They don't necessarily mean They don't have to be the same as this. Do you get my point? How many times I can shift the root beta along alpha till I get to the end of my adjoint representation? Remember, we are specifically talking about the adjoint representation here. Does not necessarily be the same. Is the same as it's not necessarily the same as how many times I can shift alpha along beta. They're two different directions, right? So this is alpha, this is beta. This tells you take beta, you can move like this along alpha, and the other one tells you take alpha, and you can move that along beta like this.
Yeah, so in one case, beta is the weight, alpha is the root, and in the other case, alpha is the
Alpha is
weight.
the weight, beta is the root. Exactly. Because after all, in the adjoint representations, weights are roots. That sounds like a trivial thing, but that gives you a rather wonderful result. So that's what I was aiming at, which I will end with. The result that you get is staring you in the face right now. You multiply the two together. What do you get? Okay, why am I so elated about this? What is this thing? Anybody? What quantity is this?
It's one.
No. Come on.
No.
Class 12. Alpha dot beta squared divided by alpha length squared beta length squared. What is that?
Cos squared.
It is cos squared. So if you take two roots, take the angle between them. By the way, the angle is defined not only in two dimensions, it's defined in multiple dimensions as well. 2 or 3 dimensions, it can be defined in any number of dimensions. There, of course, is defined via this. One thing you know for sure, that this is a cosine square of an angle. So what does it tell you about its bound? What's the smallest value? What's the largest value?
It's going to go from 0 to 1.
Yeah,
It's going to go from 0 to 1. Exactly. On the other hand, what do you know about this side? What do you know about this?
So
Again, I think you're overthinking it. What can you say about p minus q into p prime minus q prime in general?
so P was the one that we took while going up, as in the
Along alpha. Yeah.
along alpha, and Q.
Again, I think you're overthinking.
the whole,
It's much simpler than that. What do you know in general about p minus q into p prime minus q prime?
the whole number.
They are
Whole number.
exactly, they are whole numbers. Not only that, the product has to be a positive whole number because the left hand side is positive. Okay. So what are the possible values of p minus q into p prime minus q prime? Come on, this thing is bounded, right? It's between 0 to 4, and this thing has to be a whole number. Okay, positive whole number doesn't make sense. All whole numbers are positive, but you're right. Yeah, it has to be a whole number, not just an integer. P minus q could be a negative number. So could p prime minus q prime. But the product has to be a positive number.
Between 0 and PP prime.
0 to 0 and?
PP prime.
Ah, come on. Much simpler. You are making life difficult for yourself. This has to be a whole number, number one. And what's the maximum possible value?
So 0, 1, 2, 3, 4.
Exactly.
Oh, okay.
Only 5 possible values, right? Nothing else. So that tells you that no matter which semi-simple Lie algebra you have, the roots, which are vectors in m dimensions, cannot have arbitrary angles between them, can have only very specific angles between them. What are they? Corresponding to this one, What is cos square theta alpha beta? 0. So what does it tell you? So root in a arbitrary algebra, you might have roots which are at 90 degrees. You don't have to, but you can. With 1, that's 1/4, right? That means cos theta alpha beta is either half or minus half. Possible angles. 2/4. So what is it? What is this? What are the values for angles? Two by four is half, right? That's cos square. So
So does this so is this that weight diagrams that we see in particle
exactly.
physics with
Well,
so
weight
these are the
diagrams that you see are weights, not roots. But the roots are what you see in the adjoint representation, which in particle physics, when you see SU2 specifically,
Hmm.
of course, you do see SU3 specifically. SU3 has this. These are the
Okay.
angles. And because in the weight diagrams are basically vectors where you shift by the roots. Essentially, you see the same 60-degree, 120-degree angles everywhere. SU3 is a specific semisimple algebra. It doesn't have all these possibilities in it. All I'm saying is no matter what semisimple algebra you are using, whether you are using SU3 or anything else, these are the allowed angles. And 3 gives you, well, what is 3? Root over 3/4, that's 30 degrees. 4 doesn't count because 4 actually gives you cos square theta of 1. That's 1 or minus 1. That is really 0 degree and 180 degree, but you already knew that. That's alpha minus alpha anyway. Remember, you cannot have a different beta from, you cannot have a different generator corresponding to the same eigenvalue. So alpha minus alpha you already had. So these are the possible angles. So the point is, so far all we said was, okay, you have some Lie algebra, some semisimple Lie algebra. I don't care what. Okay, and you have some eigenvalues in the adjoint representation. Again, I don't care what. Some eigenvalues. And corresponding to them, you had some root vectors. But what we have established in the end, because of the SU2 structure which is hidden inside any one of these Lie algebras, you end up with this very important result. That no matter which semisimple Lie algebra you are dealing with, the roots cannot make arbitrary angles with each other. They can only make one of these 7 angles. Any 2 roots. Nowhere, nothing else. That's a huge restriction if you think about it. And of course, a particular one that you have in mind, SU3, that corresponds to this one. So there are other Lie algebras where these other things come in. We will discuss that in the next week after we. So we will essentially just show that you can sort of pinpoint the entire structure of all possible semi-simple Lie algebras just using simple algebra, like simple geometrical ideas like this. So I would ask you to pause and appreciate at this stage that this is really a rather great result. And ultimately, deriving it really took us nothing much. It just took you whatever you knew about SE2, which is what you knew about quantum mechanics. And I would submit that all of you found it a bit more difficult than it was simply because you were thinking, oh, it's the algebra, so it must be something else. Well, but all that you had was essentially whatever you had learned in quantum mechanics about angular momentum. That's it. And very simple facts. The fact that the eigenvalues have to be integers or of integers. And just as an example of how things are really simple, when you met this equation, you were all thinking about, okay, raising, lowering, what happens and so on. All you needed was whole numbers. That's it. And cos square is bounded above. That's it. So ultimately, it's really rather easy if you think of this. What we really used was what you knew about SU2 from quantum mechanics, and some very simple basic logic, and that's what gives us this. We are still a long way off because we have just figured out how the roots are aligned. Well, the weights are shifted by the roots in any representation, so that would be useful. Because so the structure of the angle structure that we have among the roots, that actually gets reflected. That's why, as you said, the SU3 multiplets that you see, the weight diagrams or the multiplets, they basically have lots of 60-degree 120-degree angles because that's the angle between the roots. Okay. And finally, we will be able to see that you can. I claim that if you knew the roots, you would know everything about the algebra. You don't even have to know all the roots. We will describe certain things called simple roots. If you know them, from that you can find out everything about the algebra. So we are going to sort of establish that in the last 2 or 3 classes that we'll hold. So I want to end today. It's already way too long. Okay. I said 10 minutes, I took 40 minutes after that. Nobody sort of complained about that. At least, I hope you didn't. I didn't hear you. But what I will do is, I will wait for you to send me the schedule for the lectures. Remember, Tuesday, Wednesday, Thursday next week.